Good evening, everyone, and a warm Cars welcome. I hope you're all staying safe and well in these trying and worrying times. I wanted to let you know what will be happening over the next few weeks at least. I have decided to hold fortnightly meetings online for the foreseeable future until we can safely meet up again for our usual monthly CAS meetings. This is to give us something to look forward to and also give us a bit of normality, astronomy wise at least. So far, I have speakers for the 18th of May, Professor Charles Cockle, Are We Alone in the Universe? 1st of June, the speaker will confirm after the 18th of May, and 15th of June, Duncan Lunin, topic to be arranged. I hope to get more speakers to be able to continue with the fortnightly meetings. If not, we will revert to a meeting once a month. But this again is dependent upon the number of speakers I can get on board. I will keep everyone updated as the weeks go on. Tonight we have Dr. Julian Onions from Nottingham University, who is no stranger to CAS, as he came and gave us talks twice before. And his presentation tonight is entitled Cold Dark Matter. Is it cold, dark, or matter? There will also be an opportunity to ask Julian questions in Zoom afterwards, as well as have a chat. Please give Julian a virtual warm CAS welcome.
Uh, oh, I'm so sorry about this. I seem to have knocked my microphone button, so I'm going to restart again. So big apologies for that. Uh, and yes, sorry about that. Thank you, the people in the chat. It's uh, right. Let me start again. Anyway, here we go. Take two. This time, I hope everything is okay. Just waiting to see if we can hear anything now. Very good. I can hear Duncan has at least addressed it. So yes, cold dark matter. Is it cold? Is it dark? Or is it matter? And just to reiterate, thank you very much to Alice Amanda for the introduction and for inviting me to talk. And afterwards, there will be a Zoom meeting, which I've just posted in the chat, to a chance to just either chat or to ask questions. So, as a slide you've seen, the plan is, why do we believe dark matter exists? What could it be if it does exist? And how can we go about finding it? So, thank you for that. So this is what we think the universe is made up of. So the vast majority of it is dark energy. By the latest calculation, 72%, 69%, somewhere around that figure. The remainder is made up of dark matter and regular matter, but dark matter outweighing the regular matter by about 5 to 1. So there's a lot of dark matter out there. Now, is this really the case? Have we just made this up? Do we? Is it the fact that we've just run out of things to discover in astronomy, so we've made something up? This is the big question. So let's see what we can find out. Right, good. I can see some people have got sound now. That's good. So I thought I'd say just in... Oh, got no sound again. No, I think people have got sound. I'm hoping they still have. Yes, hoping so. Anyway, I'm going to carry on and see if anything more comes through in the chat. As I said, it's, well, probably didn't hear that. There's about a 30-second delay between what I say and what appears on YouTube. So it takes a little while for the messages to come back. Anyway, let's see. We've been here before, somewhat, in physics. So in the 1930s, Pauli came up with this idea of a neutrino, a particle that he just invented out of sort of thin air, because at the time they were doing experiments in nuclear physics, and they found some of them were violating things that they knew and loved, such as the conservation of energy, conservation of momentum. And he said, well, we can either completely throw away these things, or we could look at doing things a different way, and I'm going to invent a particle called the neutrino, and if this exists, this will make all our calculations work again. Now, he said, I've done a terrible thing. I've postulated a particle that cannot be detected. That's Wolfgang Pauli speaking. And indeed, that was the case. From 1930 onwards, he came up with this particle, which fixed a lot of nuclear physics, but nobody could detect it. But it had a happy conclusion. In 1956, after a lot of work, I have to say, somebody did start to detect neutrinos. They are still fearfully difficult to detect even today, but it is possible now. And we do have big neutrino sort of telescopes, but anything that only captures a few of them a day gets very bad images. But anyway, he came up with this neutrino in 1930s, and it was detected in 1956. So we had 26 years living in faith, basically, that what he'd suggested was true. Now we had a similar thing in 1964 when Peter Higgs came up with the Higgs boson, and simply, came up with a particle that nobody had heard of, and we struggled on for a bit. And then in 2012, we had the confirmation that the Higgs boson did exist and had been detected. So that's another case that we've proposed something that we couldn't detect, but it seemed to make everything work, and then was later detected. So there we go. But there is some history to this. Obviously, this doesn't prove anything. We can't just go around making stuff up and hoping that somebody finds it later. But we do need a certain amount of evidence, or at least a good, solid reason to believe it. So what about dark matter? So depending on where you like to think, it was proposed in sort of 1932, which I'll cover in a couple of slides' time. And to cut a very long story short, we're still waiting for any sort of tangible evidence that there is such a thing as dark matter that we can detect in forms other than just by gravity. So it's one of those things we're still waiting for. So But let's put it into perspective. Where does it live? So if we take cosmology, which is the study of the entire universe, effectively, where does it sit? Well, all our models of cosmology at the moment, except for sort of experimental ones, all rely on a theory called lambda CDM, which is what is shown here. That's the Greek letter lambda and CDM. And what does that mean? Well, the lambda I'll talk about very briefly because there isn't a lot to talk about, and I don't know a lot about it either, so that's two good reasons not to talk too much about it. And the CDM is the cold dark matter. So this is what underpins most of our models of the universe right now, lambda CDM. And just to show you a smattering, if you go through any collection of papers that deal in any way with cosmology, you'll see lambda CDM. And I've just thrown one of my own in there just to show that I've also started a paper with lambda CDM. So lambda CDM is really where it's at, what nearly all the theories we recognize are based on. So let's just break it down a bit, lambda CDM. So the lambda bit sort of comes from, or at least is included in, Einstein's field equations for general relativity. Those equations which have a fearsome reputation, which on the whole is very well deserved because they are quite tricky and messy to solve. But you can see there's the lambda. And this side of the equation, let's see if I can draw. So this side of the equation, as it says there, says how space curves. And over this side of the equation, we have how matter behaves. And the two sort of influence each other. So that's about as much as I can say about Einstein's field equations without embarrassing myself. So we'll stop there. So what could lambda be? So there's a couple of possibilities, neither of which we really know. And there are other possibilities too, because this is all very speculative about what lambda could be, but it's the force that's pushing the universe apart. So it could be vacuum energy. So vacuum energy is caused by particles that spontaneously pop out of nothing, appear for a very brief period of time, and then disappear again. And this is entirely allowed by the laws of quantum mechanics, that you can make stuff up for free. You can borrow energy from the universe effectively, as long as you pay it back very, very quickly. And the more you borrow, the more quickly you have to pay it back. Anyway, this is a well-known phenomenon that's been tested and would give you a kind of vacuum energy that would push the universe apart. The only problem with it is it's wrong by quite a large factor. This is the factor it's wrong by. So that is one of the biggest errors in anything, really. It's a huge number that it's out by. So that's why physicists are sort of loath to take that on board, because you've got to cancel out quite a lot of those zeros to get anything recognizable today. Another possibility is something called quintessence, which is a fifth force. So we have the four well-known forces, or well, reasonably well-known forces of gravity, electromagnetism, the weak and the strong nuclear forces, and this is proposing a fifth force that is pushing the universe apart. It comes from a various derivations you can read there, and there's all sorts of ideas for it. Chameleon field is one of the ideas that we're studying at Nottingham, not by me, I have to say, by people a lot cleverer than I am. So that's one of the possibilities. There is no definitive proof for any of these things at the moment, so we're still sort of scrabbling around in the dark. So that's about all I'm going to say about the lambda side of it, the dark energy side. So now we come on to the CDM side, which I do know a little bit more about. And I have to say, I'm not a researcher in cold dark matter. I'm a user of cold dark matter. I use it in theoretical models. So that's my sort of level of understanding. So first bit is C. C is for cold. And in this sense, cold means it doesn't move very fast. We did used to have a theory of hot dark matter, and in which case that was made up of things that moved very fast. And very fast, we mean moving at about the speed of light. So, for instance, neutrinos would make a great hot dark matter candidate, but hot dark matter has been ruled out because it doesn't give us the sort of universe we want, or in fact we see, never mind want. So cold means it's relatively slow moving. It might be moving at many kilometers a second, but it's not going anywhere near the speed of light. The next one is dark, and that says it can't be seen, at least not by light. It means it doesn't interact with light in any way. So it's not really dark at all, it's more transparent. It doesn't matter what you do with light, it just doesn't see it. It's almost like a perfect window. It doesn't matter how hard you shine a light on a window. A perfect window this would be, the light just goes straight through. It's exactly the same with the dark part of the cold dark matter. And the final bit, matter, it's as opposed to radiation, so it's more of a particle than it is a sort of radiative field like light or any of those other forms of radiation, radio waves similar. And this is what we started the universe off with. So you can see it was there right at the beginning. Dark matter was 63% of the universe right at the very beginning. This is right after the Big Bang. There was a lot of dark matter around and not many atoms and no dark energy. So dark energy grows with the size of the universe, or at least that's the current theory. So there was none at the beginning, but it's been growing ever since. And this is where we are now. This is the latest Planck result. So dark energy is 68% of the universe, dark matter about 27%. And the stuff we know and love and understand, atoms and molecules and gases and the earth and the room, computers and all that, is all made out of this 4% of atoms, of which most of it is just molecular gas or ionized gas floating around the universe. About 0.5% is in stars, a tiny bit in neutrinos, and there's a very, very tiny bit in heavy elements, which is things that make up the Earth and make up the room and your body and things like that. So we are really just sort of flotsam on the wave of the universe. Now, why do we think it exists? What reasons do we have? And this goes back quite a long way, as I said, back to 1932. And the very first person to actually come up with anything that was a little mysterious was Jan Oort, who you may have heard of, a Dutch astronomer you may have heard of in a connection with the Oort cloud. He proposed the Oort cloud out way past Pluto. And amongst other things he was doing, he was looking at where we would live in the galactic plane. Whereabouts is the sun within the galaxy? Is it right at the center? Is it right on the edge? Is it somewhere else? And he came up with a reasonably good estimate that it was somewhere about halfway out. And that's about where we think it is now, about 8 kiloparsecs or 24,000 light years from the center is about where the sun is. But doing his calculations and looking at what was going on, he could only work out that there was a third of the stars needed to keep the sun in its orbit around the Milky Way. There wasn't enough stuff inside of the sun's orbit to keep the sun where it was. And so he noted this discrepancy and said, I don't know what's going on, but there should be more stuff out there than I can see. And we need to go looking for that. So he assumed it must be something that he knew about. So maybe dim stars that he couldn't see with the telescopes at the time. Could be dust, could be gas, could be all sorts of things. And we'll come on to some other things later on. So he was the first person to notice there was something odd going on. Now, the person who really sort of characterized the field was Fritz Zwicky, a Swiss American astronomer who was a bit of a wild card, to say the least. This picture certainly sums up what he does, and the stories about Fritz Zwicky are quite legendary. Go look him up if you want to find what a sort of powerful and chaotic force. But he was extremely bright, and he contributed to many areas of astrophysics. So So supernovas is something he categorized, and also this topic here. So he did this by looking at this cluster of galaxies called the Coma cluster, and he compared this cluster by two different methods, and you can actually weigh this in these two ways. One is you look at the amount of light coming from all those galaxies, and you say that, well, on average, most of the stars are approximately equivalent to the Sun. Some are smaller, some are bigger, but overall, roughly speaking, very roughly in this case, each galaxy is made up of a number of stars, and they're all putting out about the equivalent luminosity equivalent to a Sun. So if you collect all the light coming from those galaxies, you can work out approximately how many stars there are in that galaxy. And working out that each one of them is about one Sun, you can work out how much all those galaxies together weigh. So he did that, and he came up with 10 to the 12 solar masses. So that's about 1 trillion solar masses that this cluster weighs in terms of stars. But he could also weigh it by looking at how these galaxies rotate around each other, because they're all very close and they all sort of orbit around each other. And by doing this calculation, he came out with 10 to the 14, so 100 trillion solar masses. And this is a big discrepancy. In fact, it was worse than I've marked here. It's about out by a factor of 500. So even in astronomy, where we're quite flippant with errors and things, we will take things to within 10% or 50% in some cases. 500% was a little too much to stomach. So he said there is some missing matter here. There's some dark material, dunkel material, he said, dark matter that I cannot see that must be holding these galaxies together. Otherwise, they would not stick together in the way we see it. So that was really the first evidence, 1932, 33 maybe. The second one came from looking at how galaxies rotate, and this is perhaps the classic way of doing it. So if we look at how stars rotate around the Sun, nearly all the mass in the solar system is right at the centre in the Sun. Jupiter has a bit, but it's nothing compared to the Sun. So we can see there the orbital speed of the various planets. So Mercury, being very close to the Sun, is very much affected by the Sun's gravity. It would get pulled in and consumed by the Sun if it wasn't going around fast enough. So you have to be going around fast enough to sort of cancel out the gravitational pull. So Mercury whips around in about 88 days or so. But as we go further and further out, the gravity is weakened by the inverse square law. So by the time you get out to where Pluto is, which is 238 years or something like that, it can dawdle around because the gravitational pull of the Sun is so tiny out there. So it really doesn't need to be very much. And this is the sort of same thing you can apply with galaxies. A lot of the mass of a galaxy is somewhere near the middle, and then it begins to dwindle. And in fact, you can do this. This is for M33. You can see here how this starts off quite condensed, and then as you go outwards, there are less and less stars once you get between about 2.5 kiloparsecs or something like that. It really begins to fall off. So if you work out from the equations how fast the star should be moving, you can see that dashed line there. That is what you'd expect, just by the amount of matter you can see, how quickly the star should be going around. But when various people observed this, and it started in about the 1940s with someone whose name I've forgotten, but was carried on by Vera Rubin and several others, you can see the observed line there is nothing like that from the expected line. So Vera Rubin, shown here, could map this much further out, and she did this for the galaxy of Andromeda. And as we go further and further out, you can do it with gas clouds rotating around the galaxy. And you can see there, it's almost flat, the observed line, that keeps going straight out. And predicted it should drop down and down and down until we see almost nothing required. So this was a big question, and one that really did need answering, because the discrepancy was so large, and this is something on our doorstep effectively. Now, another line comes from Big Bang nucleosynthesis. So what is Big Bang nucleosynthesis? Well, this is what's worked out that happens very soon after the Big Bang. So if we look at a timeline, very soon after the Big Bang, about 1 second after, nuclei start to form. So this is nuclei of hydrogen, and other things like neutrons occur. And then the universe at about 3 minutes is extremely hot. It's cooling down rapidly, but at 3 minutes it's about the temperature of a very hot star. So stellar reactions start to happen. So things start to happen just as though you're in a big star. And you see all these reactions here. You can see P going to D going to T, it's proton going to neutron to tritium, up to helium, to lithium, to beryllium, all these things. And we can work these reactions out from laboratory experiments and say about how much of each of these should we be able to see. What rate would these things react together in a star and give us? Fred Hoyle, pictured here as one of the people who worked that out. And we help because this stops after 20 minutes. So from 3 minutes to 20 minutes, we have this fusion process is going on, making all these things, and then it stops dead because the universe has now expanded so much it's now cold. So that's something you can work out. And this is very dependent on the density of the universe. If the universe is particularly thick at that point, then you get a certain amount of stuff. If it's very sparsely populated, then obviously you don't get quite so many reactions. Not so many things bump into each other. And this gives us the following graph, which you can see, which is a bit busy, but this shows us what we would predict based on how much of various things. You can see there deuterium, that's heavy hydrogen, the amount of helium-4, the amount of helium-3, the amount of lithium. They all give us an idea of how much matter there is in the universe, essentially how close to the full density it is. And you can see this blue line going down the middle. That is what we think it is based on our measurements of how much deuterium and helium-3 and other things are in the universe. That gives us a very good idea. And you can see there it comes out somewhere around 4 and a bit %. So this is entirely different to rotation curves and similar. This is an entirely different way of working out how much stuff is in the universe. And it turns out atoms and stuff only make up 4.5% of the universe. So that's another issue. Another one is there's a big timeline here of the Big Bang to the present day. And this is something you can do with simulations. So we can put things into a simulation and we can get fairly good results. This is something I've done quite a few times in my research. So we start with the Big Bang and we put it all into a big computer and run the galaxies forward and everything like that, and you end up with what you see today. But crucially, you have to put in, it's like a recipe, you have to put in 5 lots of dark matter to every lump of regular matter. If you don't do that, you don't see the universe that is evolved today. It evolves far more slowly because basically there's less stuff around. So that's another clue that comes from simulation. If you don't put enough dark matter into the mix, you don't get what we see today. Yet another one, and this is something that Alice Amanda covers in some of her talks, is gravitational lensing. So this is a prediction from Einstein that says light is bent by heavy masses, in particular bent by stars, and in this case bent by a large cluster of galaxies. So you can see there that sitting on Earth, you can see a distant galaxy, and the light bends around those galaxies in between, and we can see sometimes 2 images of the distant galaxy and sometimes different effects. Now, again, we can work out approximately how much matter there is in these galaxies by weighing them by different mechanisms in much the same way as Fritz Zwicky does. And we also have new techniques now, such as X-rays and other ways to work out how much stuff there is in that lump of stuff that's doing the lensing here. And pretty much every time we do that, we come out with the fact that there is nowhere near enough stuff in that nearby galaxy to lens the distant one by as much as we're seeing. So this is yet another line of evidence that there is more stuff out there than we can see. And in case you haven't seen a gravitational lens, here's a particular favorite one. This is the horseshoe ring. So the blue bit is the smeared out distant galaxy, and the orange bit in the center is the nearby or much nearer galaxy that is doing the lensing. And you can see the light is all bent around there. So we don't see many of these ones where they're perfectly aligned, but we see quite a lot more of these sort, which is another one. And in this case, you can see all the yellowy, blobby things. They're the galaxies, but you can perhaps just see around here, this line here, and there's another one over here, and some more over here. These are all arcs of distant galaxies that are being lensed by these nearby galaxies. And yet again, the calculations don't add up. There is far more stuff there that's bending the light than we can actually work out from other estimates of the mass. So that's another good line. Perhaps the biggest one, and this gives us another measurement, is from the cosmic microwave background. This dotty picture looks like a rugby ball. I'm sure you've all seen it at one time or another. And you can dig out from this an awful lot of data, or at least some people can. I don't have the skills to dig it out. But what they typically do is they look at this map of this is the entire sky in microwaves, and work out how similar it is effectively over different areas, looking at different sized blobs. And this gives you, if you plot that on a graph, which is usually what ends up with, it looks like this. And you can see along the bottom, there's goes from 90 degrees to 0.07 degrees. And that says what sort of sizes are we looking at. If you're looking at the 90-degree size, you're looking at huge areas of sky that occupy 90 degrees of the sky. And by the time you get down to 0.07 degrees, you're looking at tiny areas. And you're looking at how frequently they appear to be the same. And you can see there's a big spike somewhere around 1 to 2 degrees. So on that sort of area, the sky is very similar. So now if you just take my word for it, this gives us quite a lot of information about it. The first thing it tells you is that this big spike, this gives you the geometry of the universe. So we have at least 3 geometries of the universe. It could be very spherical, a bit like living on the Earth, so that if you set off in one direction and you went far enough, you'd end up back where you started from. So the whole universe would be sort of bent in on itself. And there are other options. You could be on sort of something called a saddle, where you sort of diverge no matter which direction you go in. But to the best of our knowledge, and from this measurement, the universe appears to be flat. So if you set off in one direction, you'll just go on forever, basically in that direction. You will never come back to where you started. And that is one of the results from Planck, Planck satellite. Another one is from these 2 peaks here. I'm just going to have a quick drink. So these 2 peaks, they give how much regular matter, which we call baryonic matter, atomic matter, stuff we're all familiar with, to dark matter. And depending on how these 2 peaks combine, gives us a ratio of them. And I'll spare you the maths, but this again comes out about 6 to 1, 5 to 1 basically. That dark matter is 5 times as common as baryonic matter. The calculations and arguments to go through this are a little involved, so I'm going to skip over them, but you can certainly look it up if you wish, but be prepared for a bit of a rough ride if you do. So that's various lines of evidence that dark matter exists. And so what or at least something is missing in the universe. So how could we fix it? And there are two ways basically. Either gravity doesn't work like we think it does. Perhaps there's some defect in our understanding of gravity, and that it just works in a slightly different way to the way we think it does. This is pretty hard to come up with. We've tested gravity in many, many ways. We've flown missions out to Pluto. We've studied how stars move, and they all seem to follow our understanding of both Newtonian and, in later years, Einstein's theory of gravity. And they follow that to extraordinary levels of precision. So you can't just go and chuck in a few things to fix it. It becomes very difficult to change the way we think gravity works without ruining everything that we know and love. So that's one way. And the second way is to just say, well, there's a whole lot of missing mass. And if we throw that in, that just fixes nearly all these things. So this is the more favoured way of fixing it, although people still look at the first one, which I might mention towards the end. So there are various ways of explaining this. One was machos, there was another one with neutron stars, there's black holes, extra gas, brown dwarfs. All these things could explain it, and these are things that we know and love, we can sort of understand. So just to go through those, machos are massive compact halo objects. And in a couple of slides, we'll be talking about WIMPs. So we had WIMPs on one hand and machos on the other. So that's where those come from. Machos are basically big lumps of stuff, like huge planets or something like that, floating around, and they could fix the problem. But you do need a lot of them. The same for any of these. Neutron stars, which are the end results of very large stars. If they collapse in a certain way, they will collapse to form neutron stars. These are very tiny objects, but very heavy. So there could be lots and lots of those around. Similarly, there could be black holes. There could be lots and lots of black holes. In this scenario, they were probably produced in the Big Bang. And I have to say, they're getting very difficult to believe because we've ruled out quite a large range of the possible black holes that were produced in the Big Bang. They can't be around. It's not completely ruled out, but it's starting to be very hard to sort of fix it with those. And the other things are things like extra gas and brown dwarfs, which are failed stars and things like that. They could all, if there was enough of them, we could fix things with that. Not only have to be enough of them, but they have to be in the right places. They can't all be in the center, otherwise we wouldn't get the rotation curves we see. They have to be scattered quite freely around. But we've ruled out most of these, and this comes from yet another idea of gravitational lensing. This is micro lensing. This is more where a star moves in front of or a large object moves in front of another star. And just like you do with the big galaxies, you can do the same sort of lensing. And in this particular example, it's used to detect exoplanets. But you can also use it to look outside the galaxy and see if there are any large objects moving around, and they only have to have gravity to work with microlensing, and you would see this effect. Now it's completely random, so you can't just look and wait for it to happen. What you have to do is just look over large areas of the sky and see if you see any of these microlensing events. But given the largeness of the error, this sort of 5 to 1, you need a lot of these heavy objects floating around outside the galaxy to fix it. So even on a small sample, you can just look at distant stars and hope to see some of these lensing events. But you need to see a lot of them to fill in the missing mass. And quite frankly, we haven't seen enough of them. We've seen a few, but not nearly enough to fix the rotation curves of a galaxy. So that's sort of ruled out. And just to sort of show you what we think it needs to be, so this is a spiral galaxy like our own, and this would be its dark matter halo. So you can see dark matter is about 10 times the size of the galaxy overall. So a lot bigger all round. You need a lot of stuff and to a large distance outside the galaxy to make things work. And just for scale, here's the moon in the night sky. This is Andromeda as it would have been if you could, or would be if you could see it in its entirety. And this is how big Andromeda would look if you could see its dark matter halo. So it's a huge expanse outside of the visible that we can't see. But that does let you get this joke, which is one of the few jokes I have in this. So this is a saint with his normal visible halo, but he also clearly has a dark matter halo that's 10 times as big. Now, one quick problem with cold dark matter is if you run the simulations, which we've done many of now, and try and produce something similar to the Milky Way, you end up with something like this. So you can see the Milky Way equivalent, that's that big blob in the center, but you can see lots and lots of little smaller blobs around the edge. And these are called satellite galaxies. These are tiny galaxies like the Large Magellanic Cloud and similar dwarf galaxies surrounding the Milky Way. But from the simulations, this is called the missing satellites problem, we should be able to find about 3,000 of these small galaxies orbiting the Milky Way. And our best estimates is somewhere around 100 to 150. So we're out by a long way. So that's one of the issues with cold dark matter that has some worries about it. This can be fixed by going to something called warm dark matter, in which case you warm up the dark matter and make it move a little faster, and you get something then that's a lot more like the universe we see, at least locally. You get a Milky Way with just a few satellite galaxies, but we see all sorts of other problems from doing this warm dark matter. It's a bit like tinkering with gravity again. You get yourself into hot water very quickly. So, anyway, what could it be? You might have thinking, well, if we ruled out regular matter and we ruled out all the stuff we know about, what could it be? Surely there's nothing left. Oh no, there are many, many ideas about what it could be. So let's go through a few of the more straightforward possibilities. So the first and perhaps most favourite one is something called the WIMP, which is the weakly interactive massive particle. So weakly interacting means it doesn't really interact with regular matter much at all, much like a neutrino. It's massive, so it's quite heavy, and it's a particle. So that fits all the ticks. And the favourite candidate, perhaps, of this, probably depending on what day of the week it is the neutralino, which I'll come back to talk about. Another one is perhaps called the sterile neutrino. That's also a WIMP. An axion isn't a WIMP. We'll come back to that one too, but that's another in the top category of particles that could be dark matter. Graviton is also a possibility, probably less so. And then we get into things like the dark sector. So this is where you have dark matter particles, but you also have dark light and you have dark gravity and a whole other sort of ecosystem. And then we get to really crazy things like macros, macroscopic quantum resonators, whatever they are. There are scientific papers on all of these, by the way. And then things like cue balls, fuzzy dark matter, wimpzillas, and at this point you do wonder whether they're making stuff up. But these have all got scientific papers that have been reviewed on them saying, could dark matter be one of these things? Here's another possibility. And these all live on this particular graph we've got here. So so up the side there is there's two scales on this. One along the bottom is how heavy the particle is, and this is a huge scale. It goes from very, very, very light to very, very, very heavy. And up the side, up the y-axis, how wide it is or easy to hit. So up here at the top, we have particles we know. So here's the electron and proton, and you can see they're at this sort of mass level. A few GeV is what you're measuring in them. Don't worry about the units. So these are Up the top, they're very easy to hit. You can certainly, if you punch the table, you're hitting electrons and protons. They're very easy to hit. But down here, we have neutrinos. Ugh, it's hard to draw with this mouse. So they are much lighter than electrons and protons. We don't exactly know how light they are, but they're within that range. And they're not very easy to hit, so that's why they're very difficult to detect. They have a very small cross-section, as it's called, so that they pass through regular matter quite easily. Now, further down, we have WIMPs down here. So these are quite heavy. You can see there in this model, they're heavier than electrons and protons, but they're much harder to detect than neutrinos. And as we go down this way, we're going down in a log scale, so every step down here it's 1,000 times harder to detect. So that's why it's much harder to detect neutrinos than electrons and protons, and harder still to detect WIMPs if indeed they exist. And there's all sorts of other things that live there too. Axions are even harder to detect and much lighter. Those are over here. You can see those. Then we got these strange things like fuzzy dark matter, wimpzillas, black holes, cue balls. So black holes are very, very heavy and quite difficult to hit, I guess, because well, quite difficult to detect basically, because they're mostly black. So we've got this whole range of things, and you can go looking for any one of these, but kind of the smart money is looking for the WIMPs because they're kind of the easiest things to find. So that's where we are at, and now let's just look at a couple of them. So the WIMPs, these come out of supersymmetry, which says that for every thing that we understand, which is the basic building blocks of matter, things that build up protons and neutrons called quarks, which are over here in the yellow. So these are quarks, up, down, charm, strange, top and bottom. And then we have neutrinos below them, and the electron, muon and tau below those. And then in green we have the force-carrying particles. So the photon at the top, gluon, the Z and the W, and the Higgs. And each one of these not only has an antimatter particle, so there's an anti-up and an anti-charm and an anti-top and so on. But in this theory, supersymmetry, there is also an equivalence between the force carriers and the particles, such that we have a whole another sector, and these are called the supersymmetric particles. None of these have been found or proved or detected in any way, shape or form, and they purely come out of the mathematics of it. And they have weird names. So these on the left here, these all get an S in front of them. So they're the same as the things on the left, but they have an S in front of them. So you have squarks instead of quarks, and you have selectrons instead of electrons, as neutrinos rather than neutrinos. The force-carrying equivalents, they get enos on the end of them. So we have the photino instead of the photon, and the gluino, and the xeno, and the wino, and the Higgsino. So I say there's absolutely no evidence any of this exists, and there is an awful lot of different variants on supersymmetry, so there's a lot of things to test for. And a few of them have been ruled out, but there's lots and lots left. But anyway, if you combine these in a certain way, you end up with the neutralino, and this would be the lightest stable supersymmetric particle. So you can make lots of other supersymmetric particles, but they all tend to decay into the neutralino. So the neutralino is what's left over. So that makes a very fine dark matter candidate. It seems to have all the right properties and the right sort of abundances, and would be perfect for it. The other thing that isn't a WIMP is called the axions, and this comes out of a completely different area of physics called quantum chromodynamics, and from Roberto Pecky and Helen Quinn in 1977. They postulated the axion to fix another issue in nuclear physics, a bit like the neutrino fixed things for nuclear physics early on, that you got the conservation laws back. This does not quite the same thing, but it's a similar sort of fix, that if you include this, a lot of things come out very simply. and it also would make a very good dark matter candidate. But like the supersymmetry, we have absolutely no evidence for this whatsoever. The next one is the sterile neutrino. So we know of three sorts of neutrino. We have an electron neutrino, a muon neutrino, and a tau neutrino. But if you look at their properties, they all have a left-handed property, something sort of analogous to spin, and no right-handed property. So there is no right-handed neutrino. Every other particle pretty much has a left and right-handed version of itself. So this leads to a sort of symmetry thing again, saying, well, why isn't there a right-handed neutrino? So people have postulated that there is one, and it has a very small mass and would be a perfect dark matter candidate, because if it has a larger mass than a regular neutrino, then it would move quite slowly and would sort of fit in. But yet again, we have no proof for any of these. Then we get to bizarre things. So LKK is Lattice-Kaluza-Klein particles. So these are things that come from string theory, and they move in and out of dimensions and do things. And there's a nice little joke there from XKCD about what string theory is. So these are possibilities if string theory is correct, but we have absolutely no evidence yet again that string theory is anything other than a mathematical model. And so we don't know whether it's actually correct and is a good description of the universe as we know it. Then as we go down, these are perhaps increasingly fanciful items. They all have good solid physics underneath them, but they're perhaps not as popular as other things. Magic unicorn dust, I have to say, is my own. I haven't written a paper on it, and there is no evidence that exists either. But I thought, I want to be in with the in crowd. So this is our map of dark matter. You can see it's quite extensive. There are many, many possibilities. So it's not a case that we can't think what dark matter is. It's almost the opposite. There are too many things we can think that might be dark matter, but none of them have any direct evidence behind them other than maths, basically. So that sort of concludes the second part of the talk. And the third part is, which is somewhat shorter, is how can we detect it? And there are three ways of detecting dark matter. So we can either make it, we can shake it, or we can break it. So the first one is to make it. So this is, you go to your friendly local Large Hadron Collider and you bash particles together with as much force as you can and hope that out of the mix pops a dark matter particle and you can detect it and see it. So off you go to CERN and try all these things. And this has obviously been tried at CERN because they bash things together all the time, and they continually look for things they don't understand, which would be dark matter. You wouldn't be able to detect dark matter because it's so difficult to detect, but you would be able to see there's something missing. So that's what you would find from that. So no evidence that dark matter exists from trying to make it. The next way is to actually try and detect it directly, and for this you need to go deep underground. So dark matter, if it's much like a WIMP, it would hardly ever interact with regular matter at all. But just once in a while, it would. So, and we're talking here, with neutrinos, you get a handful of collisions of neutrinos and regular atoms a day, sort of, 10 or 20, something of that order. With dark matter, we're looking at more like one or two a week, or maybe even less than that. So if you're going to set up an experiment to detect one thing a week, you need to be quite sure you've got rid of all other sources of experimental error. So you don't want cosmic rays coming crashing into your detector. So you go deep underground to hopefully block yourself from many of the dark cosmic rays. You can't get rid of all of them, but you can at least get rid of quite a lot. So you go deep underground to tunnels like this, like mines that are over a mile deep underground, and that's where you put your detector because that gives you your best starting shot. And then you build a detector out of various things, and there's a number of different detectors that are being built. What I'm going to talk about briefly is called the Xenon the xenon experiment. So this is done by having a large volume of liquid xenon in this container here, and you're looking for collisions between dark matter and the xenon atoms. And they start off with a few kilograms of xenon, and they're quickly approaching a ton of xenon, because the more of it you've got, the more chance you have of getting a collision with a dark matter particle. And you're looking for this sort of interaction. So an incoming dark matter particle would, once in a very tiny chance, actually bump into an atom of xenon like this, and the atom of xenon, like this one, would then go shooting off in this direction or something like that. On its way, it would bump into other atoms, knocking electrons off them, and you get a very small electric charge, and you get a very small increase in the temperature, both of which they've done extremely fine experiments to be able to detect. So that's what you're looking for, something like this. But there's so many other things that could also do this. Neutrons would do this equally well. Radioactive decay would also trigger this. So you have to build your detectors out of the purest things you can and try and screen for all these things. And what we end up with after doing lots and lots of these experiments is this very, very busy graph. So this is the same as the one I showed you back a while ago. Along the bottom here we have how heavy the particle is, and down the side we have how likely it is to bump into other things. And all these lines on the graph, the dotted dashed lines, these are all different experiments. And so if we pick one, such as this COOP one up here, what that solid green line means that dark matter cannot exist in this area of the graph. Oops, sorry, I've gone over the lines. I'm not very good at colouring. So that said, we're sort of 99.999% dark matter. If it was in this range of heaviness and this range of collision cross section, we would have found it by now. So we've worked out it doesn't exist in here. So we've got a lower bound on the cross section and a range of mass that it can't be. And you can see with each of the bigger experiments, you're pushing those lines further and further down. So down here we have the xenon 1 ton experiment down here. So that's obscured it all above the green line. And you can also see here a faint circle. This is what supersymmetric theory predicts the particle would probably be in, at least under some variance of it. So that's kind of where they're pushing down to try and find it. And as of yet, there has been no signal or no detected occurrence of it. There are other ways of things. So the axion, as I said, would be much, much harder to detect than the WIMP. But luckily, there's a kind of cheat with axions that they interact slightly with magnetic fields, and you can turn axions into light by passing them through strong magnetic fields. So this is a way of running an axion detector. You try and look for a light signal that's passed through effectively a solid brick wall, and if you can, then with the large magnetic fields, and that's a way of detecting it. Likewise, no detections from that. And finally, there is another way of detecting it, which is the fact that comes from the theory being that dark matter is its own antiparticle. If two dark matter particles run into each other, they will annihilate each other, much like matter and antimatter do. But given they have this very tiny cross-section of bumping into each other, it's going to be a very rare occurrence. So what you do is you look for it in very dense areas of where dark matter should be. So the center of the galaxy, for instance, that should be the densest area of dark matter. So you look there and you look for signals in the electromagnetic spectrum of signals of dark matter annihilating itself. So it should give off something quite energetic, something like an X-ray or a gamma ray, and come shooting out of the center of the galaxy, because that's, if anywhere is going to have interacting dark matter, that is where it's going to be, probably. They've done lots of these experiments. They occasionally find strange spikes coming out of the center of the galaxy. The trouble is there are lots and lots of other things in the center of the galaxy that can also give off these strange spikes. So black holes, neutron stars, pulsars, all these things can give off strange radiation. So you have to try and work out a model for the center of the galaxy and work out how much of each of these would be and subtract that off and see if you've come up with anything. And so far, there's been no conclusive case for this occurring. Now, going back a long while, I said you could get rid of dark matter by having alternatives by fixing gravity. And there have been some attempts of this, and they are somewhat successful in some cases. So perhaps the most well-known one is done by Israeli physicist Milgrom and his MOND theory, modified Newtonian dynamics. So he took the second most famous equation in all of physics, F equals ma, and changed it to this form here, F equals m with a function based on a and so on. And with the constraints that if a, which is acceleration, is much, much bigger than a naught, which is an acceleration chosen, then basically this whole thing degenerates back to F equals ma. But if the acceleration is much smaller than this a naught he's picked, then it becomes this other variant called F equals ma squared over a naught. And if you go with this, then galaxies behave perfectly. They rotate perfectly. But in a sense, it was designed to do that because he went looking for a value of a naught that would make it all work. And this is what he came up with. So it's certainly a way of sort of fixing at least one of the problems. It fixes the rotation curves. It doesn't really fix some of the other cases, Big Bang nucleosynthesis, gravitational lensing, cosmic microwave background. There have been attempts to try and fix it with this. And so, it is another option, but not one that's really taken the mainstream at the moment. There are still people working on it, though, which is good. I mean, we always want to keep our eye on the possibility. There are a few issues with it. It doesn't always satisfy some conservation laws, such as momentum, and it doesn't really cope with relativity. So going at high speeds, it doesn't really work. And there are, say, a few other issues. So people have tried to fix that. Tevez is one of these. Tensor vector scalar gravity is also another one. And these are all generalizations of MOND that are supposed to work with relativity. But there are other issues. Some people think stars may be unstable under Tevez. So, that's not a good idea. And you can see there's almost as many options for this as there are options for dark matter particles. But they're very difficult to come up with because, as I say, gravity is very well researched and quite well understood as a force. So if you're going to mess around with it, you've got to make sure it works in all the conditions we know currently and not break it. So just to wrap up and answer the three questions at the beginning. Cold dark matter. Is it cold? Probably not. It could well be, but it could be warm, as we've seen there's a case for warm dark matter. So that's a possibility. Is it dark? No, not really. It's much more transparent. Dark is a really bad name for it, but it's one we're stuck with. And does it matter? It's not really. I think it's really some other sort of thing. When we finally pin it down, if we do, then perhaps we'll be able to give it a better name. But until then, we're stuck with cold dark matter. So I'd like to thank you all for listening, hoping somebody is out there listening. And at this point, we're probably going to swap over to the Zoom call. I've posted the link in the YouTube chat. So I'm going to start that up in just a few seconds. Give you the 30 seconds to catch up. And then we can take it from there. And feel free to ask me any questions or just have a general chat and just to see everybody for once in this lockdown scenario. So perhaps see you over there.